Welcome back all to another lesson on sequences. Today we're going to be looking at a new kind of formula called the recursive formula. The recursive formula is a little different from what we've done before in that the formula is actually used to find the next number in the sequence given that you know the previous number. Okay, so let's first actually do a review of what we've done before. Let's take a look at the sequence here that we see. 7, 15, 23, all the way until k or even n. Now, as I were to look at this sequence, I can see that as I go from number to number, it looks like I'm adding 8 each time. So this is telling me that I'm going to have some kind of arithmetic series, or sequence rather. And because I know it's arithmetic, I know that my equation, my formula should look like in the form of some kind of mx plus b. Okay, so as I just kind of lay everything out, I know that, I have everything always increasing in values of 8. Remember that the 8 is the common difference, or another word for that is, it's kind of like the slope in your formula of your mx plus b. Since the common difference is 8, we're adding 8 every time to each term number. Remember that x represents that term number. Okay, so therefore it's 8 times the term number, which we'll call n, and plus the starting value. Now the starting value is like if you were to look on a coordinate plane, remember it's kind of like that case number 0. So where are we at the case number 0? Well, if we were to go 8 back from 7, that would take us to -1. So actually we need to turn this into a -1. So 8n minus 1 is going to equal our nth term, whatever that is. Okay, let's take a look at number 2. Do the same exact idea here. In looking at this pattern, we have 3 terms. We have 1.5, 3, and then 6. Now, how do we go from term to term? It looks like what we're doing is from 3 to 6, we're definitely here having to multiply by 2, right? It looks like every time we're multiplying by 2. So for that reason, this is telling us with that common ratio, because it's a common ratio, we now know that this is going to be a geometric series rather than the arithmetic we saw up above. So if it's geometric, we know the common ratio multiplied by 2 is what's occurring every time. And if you recall, our geometric formula was created by doing the first term multiplied by that common ratio taken to the power of n minus 1. And so in this case, to find the nth term, our first term is 1.5, or I'm just going to actually say 3 over 2. Okay, that's our first term, times the common ratio being 2 to the power of n minus 1, like that. Okay, so these are the formulas that we've come up with in the past. It turns out that these formulas have a name. These formulas are basically called finding the nth term of the sequence, and we give that the name the explicit formula, because you're explicitly finding the value at the nth place. Okay, so that's the explicit formula. Now compare that with what we're going to now study today, which is the recursive formula. The recursive formula is used to find the next term if you're given the previous term. Okay, so that's what we're going to look for. Given the previous term, how do we actually get to the next term? So let me detail what that exactly looks like in example 1 and 2. So I'm going to use a different color here. Let's actually use blue, or is blue too confusing? Let's use red. That way it doesn't blend in with the purple. All right, so with this sequence here, imagine that we actually didn't know the number of 23 or 15. Instead, we only know the number 7. So what you're asking yourself is, what is this value here? I don't know this value. So what do? We take what we know from before, which is 7. We take our previous term, 7, and then add 8. We add 8 to get 15, like that. Okay? Well, now I don't know this number. How do I find this number? I take my previous term, 15, and what do? Add 8 to it. That'll give me 23. Okay, so that's the idea behind it. When you create your explicit formula, you're saying if I want to find that term, then what I'm going to do is take my previous term. How do I represent that? If this is term n, then my previous term must have been t sub n minus 1. I take my previous term. What did I do to it? I added 8 each time. That's my recursive formula. T sub n is the previous term, t sub n minus 1, plus 8. Okay, let's take a look at example 2. Here, again, I don't know these numbers. I don't know the 3, I don't know the 6. So instead, let's say, okay, I don't know this number. What do? I take my previous term, 1.5. What do I do to it? I multiply by 2. That'll give me 3. I don't know this number. I take my previous number. What do I do to it? I multiply by 2. I'm always multiplying by 2. So this is saying if I don't know a term, then I take my previous term, which is the t sub n minus 1. What do I do to it? I multiply by 2. So this is 2 times t sub n minus 1, like that. That's the recursive formula. So when using the recursive form, there's one caveat to this. You need to make sure you also define the t sub 1 value, the first value. If you don't define it, you might actually just get a completely different sequence, which means up above, if I had this formula, I need to also say that t sub 1 was the value of, what was my first term? It was 7. And what was my first term in number 2? It was 1.5. So over here, I'm going to say t sub 1 is 7. My first term is 7. Now this is a complete recursive formula. Okay, and what was the other one? Number 2, t sub 1 was a value of 1.5. So I make sure I define my t sub 1, and then that's going to be the complete recursive formula. Okay, let's see why it is so important that you state what t sub 1 is. Let's look at number 3, a and b. Look at this. Okay, I don't know what these are. 1, 2, 3, 4. I have the values of 1, 3, 5, 7. Again, but I don't know these. I don't know 1, 3, 5, 7. All I know is 1. I need to know this. How do I find it? I take my previous term and what do? I'm adding 2. That's how I end up to get 3 here. I don't know this term. What do? I take my previous term and add 2. So in the recursive form, what I'm saying is I don't know this term. What I do is I take my previous term, t sub n minus 1, and what do? I add 2, like that. Okay, so therefore I get 5, and then I get 7. Well, likewise, in letter B, let's do it again. 1, 2, 3, 4, and then we have 2, 4, 6, 8. Again, I don't know those numbers, 4, 6, 8. So what do? I don't know this. I take my previous term, and how do I get there? I have to add 2. That's how I'll actually get the 4. I don't know this value, so what do? Take the 4, add 2. Well, that'll give me 6. I don't know this, so I take my previous term, add 2. That'll give me the 8. So you can see that if I want to find a term, I take my previous term, and what do? Add 2. Oh, look at that. But that's weird. I get the exact same formula in both 3a and 3b. This is why it's crucial to say what t sub 1 is. If I actually get that the first term is 1, now I get the sequence 1, 3, 5, 7. If I got the first term to be 2, now I get the sequence 2, 4, 6, 8. So it's really important you state what t sub 1 is. Okay? All right, let's take a look at some more problems here. Write a recursive definition for this sequence. 1, 3, 6, 10, 15. Wait, that sounds familiar. We've done this before, but what we did was we actually found the explicit formula. If you recall, the explicit formula was that n times n plus 1 all over 2. But this is not what we're looking for. We're looking for the recursive formula. Okay, so let's go ahead and build our table out of this. We have 5 terms. 1, 3, 6, 10, 15. And what we want to ask ourselves is, how do we get from term to term? Imagine, I don't know this value of 3. If I need to find that value of 3, how did I get that? I got 1, and then I added 2. That's what gave me my 3. Okay, now let's go to term 3. I don't know term 3. If I don't know term 3, what am I going to do? I take my previous term, and then how do we get here? We actually add 3. That's how we got to 6. So at term 3, I had to take my previous term and add 3. Over here, I kind of don't know that 10, right? So if I don't know 10, I take my previous term. Here I am. I want to find term 4. I want to take my previous term, and what do I add? I have to add 4. Then I actually get the value of 10. Okay, well, now I'm at term 5. I don't know term 5. So what do? I take my previous term, and I add 5 to get 15. Hopefully, I'm trying to emphasize this over the recording, but hopefully what you see is that if I'm at term 2, I take my previous term and add 2. If I'm at term 2, I add 2. If I'm at term 3, I take my previous term and add 3. If I'm here at term 4, I want to find this value. I take my previous term and add 4. Hopefully the idea you see here is that if I'm at term n, I take my previous term, which is t sub n minus 1, and what do? I add the n value. I'm adding this 4, I'm adding this 3, I'm adding this 2. You're adding wherever you want to find it at plus n. And then don't forget that last step. State what t sub 1 was. In this case, t sub 1 was 1. That's going to be your recursive formula. Compare that with the explicit formula. Notice they are not the same. Okay? All right, let's go on to number 5. All right, so for number 5, we have the sequence with 1, 2, 3, 4, 5, 6 terms. I'm just going to go ahead and write 6 terms here. Build a table. We got 1, 3, 7, 13, 21, and 31. All right, let's do this again. Remember, you're kind of imagining you don't know these numbers. I don't know why I wrote them. I'm going to erase it. I'm going to say, I don't know this number. What do? I take my previous term. So you know that in terms of a recursive formula, you're going to say, if you want to find the nth term, you got to take the previous term and do something with it. So t sub n is equal to t sub n minus 1, and let's see what we did. Over here, if I don't know this term, it's really 3, right? I'm going to take my previous term 1, and what do I do to it? It looks like I have to add 2 to get there. Okay? Interesting. Okay, then we need the next term. Well, 3 needs to add how much? We need to add 4 to get to 7. This isn't quite the same. We're not saying let's add that nth value, because you can see here 3 is not the same as 4. Let's keep going though. If we want to go from 7, don't forget, if you want to get to 13, then to get from 7 to 13, we need to add 6, right? Okay. Then to get to the next number, I don't know this number. I sort of know it's going to be 21, but how do I get from 13 to 21? How do I get to my next term? Well, 13 plus 8 is going to give us our value of 21. Over here, this is supposed to be 31, right? How did I get there? I got from my previous term and added 10. Okay, so we're saying let's take our previous term and add something. Well, what's that something? That something is either 2 or 4 or 6 or 8 or 10. Well, hopefully what you're saying to yourself is what we're doing is we're basically adding some kind of even number, huh? How do we get even numbers? Even numbers are always multiples of 2, right? So we're saying take the previous term and add 2 times something. Well, how are we going to get 2 here? If I want this at term 2, then I need to add 2 times something to get me 2. 2 times what? Well, that would be 2 times 1, right? This is the same as 2 times 1. Okay, this right here, if I don't know this term, I take my previous term and add 4. How do I get to 4? Well, this is the same thing as 2 times 2, right? Then how do I get to this term? I need to take my previous term and add 6, which is 2 times 3. So if I want this term, hopefully what you can see here is I'm taking 2 and multiplying it by it looks like it's actually going to be, let me do this in a different color. It looks like that 4 is technically 1 less than 3. Over here, when I needed 7, I take my previous term, I add 2 times 1 less than 3. You see that? 1 less than 3. Over here, if I needed this number, I take my previous term and add how much? 2 times 1 less than that 2. So it looks like I'm taking the 2 and multiplying it by 1 less than the n value, like that. Okay, and then just make sure you also state what that first term was. T sub 1 was 1, like that. Okay, all right. Let's go on to the next page. All right, number 6. Let R sub n represent the number of regions formed when n lines are drawn in a plane such that no 2 lines are parallel, no 3 lines are concurrent, which means meet at one point. Find the recursive formula for this and also find the explicit formula. So we need 2 formulas here. Let's first actually draw this representation, the number of regions. Now we're going to make our rectangle the space, the plane that involves these r's, okay? Now r sub n represents the number of regions formed when n lines are drawn. So the first case is if you just draw one line, right? If we just draw one line, then r sub 1, just draw one line. How many regions do we form? We form one region here and 2 regions here. So r sub 1 is the value of 2 then, okay? Let's do another case. If we now draw one more line like this, then notice what we form. We form one region here, another region here, another region here, another region here. So it looks like when we have 2 lines, we form 4 regions like that. Okay, we can keep this going. Remember, no 2 lines are parallel, no 3 lines are concurrent. So if I draw another plane, one line here, one line here. Now no 2 lines are parallel, so I can't draw a line here like this. What I want to do is maybe something like that, where no 3 lines meet at one point. That means, let me erase this actually. That means I shouldn't be drawing a line like this, right? Because then they'll all meet at one point. That's not what I want. Okay, so something like what I drew earlier like this would be perfectly fine. Okay, something like that. How many regions do we form? Let's see. There's 1 here, 2, 3, 4 here, 5, the space right there, 6, and it looks like we have 7 regions, huh? So r sub 3 is going to be a value of 7. Let's draw another one. Let's see here. And let's go with 4 lines now. So 1, 2, 3. Now how am I going to make a 4th line so it's not parallel with anything and not concurrent with 2 other lines? Maybe something like this, like that. How's that look? Pretty good. It's not parallel with anything. It's not meeting up with 2 other lines. It looks pretty good. So let's label it. I'm going to do this in a different color so you can see. Notice we have 1 space here, 2 there, 3 there, 4 here. It's kind of hard to see, but there it is. We have 5 here, 6, 7, this little space here, 8, 9, this triangle, 10, 11. Looks like we got 11 spaces. Okay, now do be aware, depending on how you draw this, you might not be able to see a particular region. Let me just do it again. If I did a smaller space, something like this, maybe like this, and then, I don't know, maybe do another one like this. Okay, so if I did this, imagine what you would see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you might be asking yourself, well, I only see 10 regions here. But remember, in geometry, planes are infinite spaces. So you got to imagine that these lines actually do keep on extending on infinitely. And if they do extend infinitely, then eventually these 2 lines will meet, right? And when they meet, you're going to have this entire region be region 3, but then you're going to have this little region right there actually going to become another whole region. That's where the 11th region takes place, over here on this side like that. Okay, so do be aware of that. Be careful when you do draw these. Okay, so it turns out that in terms of having 4 lines, we're going to have 11 regions here. Okay, all right, so with that said, let's go ahead and use these numbers and build our table. We have 1, 2, 3, 4 as our term numbers, and notice the values that we now have are 2, 4, 7, and 11. And these are the numbers we want to use in creating both the recursive and explicit formula. So let's get to it. Let's do the recursive formula first. How do we do that? To get to, from, we don't know this value, 4. What do? We take the previous number and add 2. We don't know this number. Here's our third term. We take our previous number, so let's say t sub n. I don't know this number. I take my previous number, which is t sub n minus 1, and add 3. I'm at term 3. I want to add 3. Here, I'm at term 4. I don't know this number. I take my previous number and, what do? Add 4. At term 4, I take my previous number and add 4. So it looks like we're adding that n value again. What's our first term? Our first term is 2. So there's our recursive formula. Make sure you specify, because now we're going to create the explicit formula. Okay? When it comes to the explicit formula, I'm just going to go ahead and make my table again. 1, 2, 3, 4, 2, 4, 7, and 11. When it comes to the recursive formula, I'm adding 2, adding 3, adding 4, and then I add 1 and add 1. So remember, common difference occurs the second time around. That's telling me I've got some kind of n squared. So something times something gives me these values. Let's figure that out. What gives us 2? 2 times 1, right? What gives us 4? 2 times 2? Let's see if that works. Obviously, this is not going to work, though, because 2 and 2 occurring together, that's probably not what's happening here. What gives us 7? Oh, man, this is not working out, is it? 11. Hey, wait a minute. As I look back at this, I do see 2, 4, 7, 11. It does kind of mimic what we've seen before. Doesn't that look like, hopefully you're saying it, 1, 3, 6, 10? Add in another 15 there, right? What we're doing is we're taking that number and subtracting 1 by it. 4 minus 1 is 3. 7 minus 1 is 6. So it looks like we can use this sequence again. What was that sequence? It was n times n plus 1 all over 2. That's 1, 3, 6, 10, 15. And we need to take these numbers and make them 2. Make 1 into 2, 3 into 4, 6 into 7, 10 into 11. So what are we doing? Adding 1 to it. This right there is our explicit formula, like that. Okay? All right, so that takes care of number 6. Let's do our last problem here, number 7. Each day, 8% of a quantity of radioactive iodine will decay. Use a recursive equation to show this is happening. Well, recursive just means we don't know what a value is. Let's call it quantity Q sub n. At this particular value, what are we doing? Well, we're taking the previous value and doing something with it. Do you remember how radioactive iodine decays? It's decaying at 8% of its quantity. Well, what does that mean? Well, I have 100% here, and after that, I'll get to how much? Like 92%, right? After that, what am I doing? I'm multiplying that by 92% of that because it's decaying by 8%. What do I do then? I multiply by 0.92, right? I keep multiplying by 0.92 because it's decaying at a rate of 8%. 0.9 multiplying by 0.92 is the same thing as taking away 8% each day, okay, or each time, whatever that unit is. Okay, so for that reason, we have to take the previous amount, and what are we doing to it? We multiply it by 0.92, like this. Okay, so that's going to be our recursive equation. Now, what is Q sub 1? I don't know. It doesn't say. So let's just say Q sub 1 is just some question mark. Okay, so that's going to be problem A. Find the approximate half-life of this iodine. Well, remember what half-life means. That means you want how long does it take to get to half of its amount. Okay, so if we know that we start off with 100%, and then we know in one time frame, you multiply that by 0.92, right? That'll give us 92. And then let me actually take my calculator out here. Okay, so now we know to go to the next term, we need to go from 92, multiply that by 0.92, and we're going to get a value of 84.64. That's multiplying by 0.92, right? The idea here is basically when we keep multiplying this, how long will it take to get to half the amount? So la-di-da-di-da. When do we get to about 50, right? We want to find that half-life. So let's just go ahead and do that. Let's figure that out. Go ahead and multiply that. 84.64 times 0.92. And we get 77.868. And then we multiply again by another point. Let me erase all this actually. Times another 0.92. And we get 71.64. And then another one times 0.92. We get 65.91. And then again times 0.92. What do we get? 60.63 again. And we get 55.78 again. And we get 51. Look at that, we're getting really close. And then again times 0.92. And looks like that'll do it. That'll give us 47.22 basically. So it's occurring somewhere between here, right? Well, how many times did we do that? 1, 2, 3, 4, 5, 6, 7, 8, 9 times, huh? We went from the 8th time to the 9th time. So what we're saying is going to take about 8.5. Maybe this is in days. I'm not quite sure. Let's just say days, okay? So it doesn't have a unit of time, but we're just going to assume that it's days. So it's going to take about 8.5 days, okay? Likewise, that was kind of a long way to do it, huh? Likewise, we could have also just said, let's take some initial amount, let's call it Q, and then we're multiplying it by 0.92, some number of days, right? Some unit of time. And we should end up with half of our original amount. That's another way you can do it. Now, if we solve this, notice how Q is on both sides. Divide both sides by Q, and really that just goes away. So what you have is 0.92 to the D equals half. Remember how to solve for D? We can log both sides, bring the D down, like that. So you get log of 0.5, and then your calculator. Let me actually just pull up my calculator here. Calculator, let's do Desmos. So then I want to do log of log. Where is log miscellaneous? Here we go. Log of 0.5. And then what I want to do with that is, if I recall correctly, I want to divide that. Oops, not like that. I want to take that answer and divide it by log of, I believe it was 0.92. So I'm going to say log of 0.92. Log of 0.5, oops. Log of 0.5 over log of 0.92 is actually 8.31 days. Let's go back, 8.31 days. Okay, so notice here, when we solve for the value of D, log of 0.5 over log of 0.92 is giving us a value of about 8.3 days. Let's call that days for the units, okay? So it's really going to take about 8.3 days. There we go. Okay, so that concludes our lesson on recursive formulas. Let's meet up in Zoom. See you later.